Okay, so here we go. Here are just a few problems from homework. Not everything, but just a little bit of stuff to kind of give you some help if you're stuck on some things, and just kind of to reiterate some of the bigger stuff in class. So anyway, the first thing is doing limits with infinity for exponential functions. The key to exponential functions is basically wondering this. Am I going to get some number to, or basically some number to infinity, which blows up to infinity, because they're, or is it going to be some number over infinity, b to the infinity? Because that basically just gives us 1 over infinity, which is in 0. So those are the two things you kind of have to sort out when you're doing limits involving exponential functions. So so this one is exponential. It's continuous. I can just plug it in. So what I have to realize is I have 1.001 to the negative infinity, which means that I really have 1 over 1.001 to the infinity. Now this number is bigger than 1, so that means it's going to blow up. So this gives me that case of 1 over quote unquote infinity, which has a limit of 0. And then on 26, a similar thing happens. You get e to the negative x squared. Well, that's really the limit as x approaches infinity of 1 over e to the x squared. Okay, great. That really means you have then 1 over e to the quote-unquote infinity squared, which isn't possible. But this is just going to blow up to be a bigger form of infinity. So we're still going to get this 1 over quote-unquote infinity equals 0. Now the next example type is what to do with rational functions going towards infinity. Okay. And there are all these little, we looked at a bunch of examples in class and like a lot of little tricks. And the trick for this is to look at the denominator and find the highest power of the denominator. Okay. And divide everything by that. And the reason we did that was what it does is it cancels and simplifies to base the idea that if I get 1 over x or some form of that, or really a number over x or some form of that, where it becomes number over infinity, that limit goes to 0. Okay, so we're going to hopefully cancel off all these terms, if anything, and then get to look and see what we have left over. So what this really becomes in is the limit as x approaches infinity of 3 over x squared plus 20 over x cubed all over 2 plus 3 over x minus 29 over x to the fourth. So now when I plug infinity in for x, this guy essentially goes to 0 because it's 3 over some form of infinity. This goes to 0 limit-wise. This goes to 0, this goes to 0. So each of those basically then become limit as x goes to, or sorry, becomes 0 plus 0 over 2 plus 0 minus 0. Well, 0 over 2 is 0 for our limit. So that one's 0. Okay. Next one we're going to take a look at. Okay. Again, we're looking for the denominator's polynomial highest power. This is just a plain x, so divide everything by x. And again, as long as I do it to everything, I'm changing the form but not the value. So this becomes then limit as x goes to infinity of 7 minus 9 over x over 4 plus 3 over x. And then what happens is, oh, again, plugging that infinity in, number over infinity becomes 0. Number over infinity becomes 0. So for us, limits-wise, we can say this is equal to 7 minus 0 over 4 plus 0, which is just 7 over 4. So there's our limit. And then last case for this, because these are one of the three cases. Again, rational function, both polynomials. So what we do is we divide everything by the highest power on the bottom. Okay. That gives me limit as x approaches negative infinity this time of 2x plus 3 minus 31 over x cubed all over 8 minus 31 over x squared plus 12 over x to the fourth. Okay. Now, when we look at this, again, this goes to 3, so it's a nice whole number. This goes to 0, because it's going to be something over infinity's cube, so it's be something over a giant number, so 0. This also goes to 0, this also goes to 0. Okay. But this guy, right here, he's the key to everything. Because I have this power on top that's going to keep growing and growing and growing. What I'm really going to get is something like the quantity 2x plus 3 over 8, which is akin to 1/4 x plus 3/8. It's not going to look exactly like it, but it's going to, if you were to graph it, you would see it kind of approaches almost like a line for an asymptote, like a line for an asymptote. So what that means is this guy's never going to stop growing because he's a line. And he's got a positive slope, so he'll look something like this over time. Oops, I'm running it. I put it this way. And since I'm going to negative infinity, it means I'm going to the left this way. So this guy's going to go to negative infinity. Okay. So it doesn't have a limit, but we'll describe it by saying it goes to negative infinity. Now here's one of the things to be careful with. You've always got to, when you pick a variable to divide everything by, you've always got to go with the denominator's biggest power. If you just pick the biggest power you see, divide everything by an x to the fifth, let's say, 2x to the fifth over x to the fifth would give you 2. This would give you plus 3 over x minus 31 over x to the fourth. This would give you 8 over x minus 31 over x cubed plus 12 over x to the fifth. Again, this is wrong, but you've got to make sure you always use the denominator, because again, if you just choose arbitrarily biggest one, what you would get for this limit is, oh, I'll plug in negative infinity, I would get 0, 0, 0, which is undefined. We might say, well, it's going to blow up then or something like that, 0, 0, and then you get positive 2. So what this might tell you is, oh, 2 over some arbitrarily small number close to 0, oh, it goes to positive infinity, which it does not, because this guy stays with the x and he's going to grow towards negative infinity because I'm plugging a negative in. So you got to make sure you choose the biggest of the denominator, not the biggest total. Okay. All right. Now, the next problem, there are kind of two ways to think about this. One is an intuitive way, which I'll show on the next. I'll do it a second time. The other way is the actual operational way. Now, for this problem, okay, the denominator is x cubed. The problem we have, though, is on top I have a square root. So what I've got to do is I've got to find a way to get this inside of a square root. Well, the way we do that, okay, is we think of this, yeah, they're kind of, well, there's two ways. I'll show you in the next one. The first way is just to say this, okay, I'm going to divide this by x cubed. I'm going to divide this by x cubed, because again, whatever I do to the inside, I have to do, or whatever I do to this guy, I have to do to all of them. It's the biggest power. But what I've got to say to myself is, okay, in order to get into a square root, I have to divide by something that if I took the square root of it, would give me x cubed, and that's going to be then x to the sixth. So to put in the square root, I'd have to divide everything by x to the sixth, not x cubed, which I'm sure some of you will make that mistake and say, oh yeah, x cubed is the highest power in the denominator, divide them by that. No, I've got to make it inside of a square root. In order for that to happen, it has to be an x to the sixth, not an x cubed. Now what happens to us then is, limit as x approaches infinity, I get 4 plus 1 over x cubed on bottom. Okay. On top, I get the square root of 9 over x squared plus 3 over x to the fifth plus 2 over x to the sixth. And then what happens is when I start plugging those numbers in, okay, I get 0, 0, and 0 for those, because it's going to something over infinity. 0 here. I really get the square root of 0 plus 0 plus 0 over 4 plus 0. Oh, square root of 0 over 4 ends up being 0. Okay. Now, the other way I could argue this one is this. Let me imagine for a moment, again, kind of going back here, and if you haven't noticed this pattern and I didn't spell it out in class for you possibly, because I don't spell everything out all the time. if you'll notice on these problems like this, the only thing that really ever matters is the two highest powered terms, the one on top and the one on bottom. This guy, the lower ones always cancel off to be 0, even if this one isn't 0. In this case, it was 0 for both of them because they end up not simplifying enough. Okay, but I don't really need to worry about the rest of the junk. I really just need to worry about these two terms, and we'll come back and talk about this when we talk about the third day with asymptotes, because that's kind of what you do with asymptotes. So really, the only thing I have to worry about is what's going on with these highest powered terms. Okay, well, the highest powered term versus this one, let me think about how I get this together. Well, I would square this, and I could throw a square root around it. Okay, that would make them both be under the square root. So what I really have is, like, I think of a giant square root of 9x to the 4th plus 3x plus 2. Now, if I squared this guy out, again, there's, I could do a bunch of work, but the easiest, this is a binomial, so it'd be 16x to the 6th plus 8x cubed plus 1. That's what it would actually work to. So what you might catch as a shortcut is, oh, I'm going to divide everything by x to the 6th. Okay, this is going to cancel, these are going to cancel. I'm really just looking at these two guys. And the question is, which one grows more, top or the bottom? Well, the top grows less because it's only x to the 4th. Bottom grows faster, so I'm going to have something over basically an infinity. That's another way to kind of intuitively look at this and go, oh, it's going to just be 0. Because the top won't keep up with the bottom, so we'll go to 0. And again, we'll come back and talk about this on the third day. Okay. Now, the last example I want to take a look at from this section, hopefully is an easy one. We've done this a few times now, but it's just something we have to talk about again, is absolute value functions. Okay. So with absolute value, it doesn't matter what you do for any of this. The first thing you have to realize is, what's my domain? What am I doing? Well, I'm going towards negative infinity. Okay, second thing is split this up into piecewise function. The absolute value function is x if x is greater than 0, because if you take the absolute value of like 7, you just keep 7. Now if it's negative, like negative 3, you do the opposite of x, because the opposite of negative 3 is positive 3, because again the key is we want the absolute value to always be equal to 3. Well, since we're looking towards the left, that means we're working with this form of the absolute value function, so I need to replace this guy with negative x. So the limit as x approaches negative infinity of negative x plus x over x plus 1. Oh, well, look at this on top. Isn't that nice? That becomes 0. So no matter what I do, I'm going to get, again, I'm going to have negative infinity plus 1. So I'm going to have 0 over really basically negative infinity. Doesn't matter. Still 0 in the end. Yeah. So again, if that doesn't make sense, I know this is a weird section. There's a lot of little weird tricks, it feels like. Come in. Hopefully this helped out some though, to get you at least through a part of the homework. And yeah, so again, come in if you have questions.